So as I said, I want to wrap up this series of lectures, roughly speaking, introducing the duality web. I started off with lecture 1, which basically motivated why we want to study these problems. Lecture 2 was focused on 3 dimensions. That's 2 spatial dimensions and 1 time. So 2 plus 1 dimensions, in which I showed how the ideas of bosonization leads to, or multiple applications of the idea of bosonization leads to this whole intricate web of dualities that was discovered in 2016. And one of the, uh, one of the really interesting developments here is that these dualities are non-supersymmetric. And the fact that they're non-supersymmetric is a big deal because because they lead to a number of relations between low-dimensional field theories, which were subsequently exploited by condensed matter physicists and led to an enormous development in the idea of topological quantum materials in the condensed matter setting, and a number of interesting developments in the high energy physics or formal quantum field theory setting. The physics in the 4-dimensional story is not as clean, and it's not as clean for a number of reasons that I'll try and outline as we go along. One is certainly that I can't use the differential geometric language of forms in 4 dimensions anymore, and that's a matter of convenience or inconvenience in this case, because there are a number of different contractions that I'm going to need to use, and we just haven't, or I just haven't figured out how to think about this in a clean differential geometric way yet. This is one of the things that I'd like to pursue in greater detail, though. Okay, so I need to insert some pages. Delete that. Okay, so I finished off last time essentially here where I demonstrated a Fermi-Fermi duality, starting off from a Bose-Fermi duality. So starting off with a bosonic theory, I can fermionize that theory, and then I can fermionize that theory again, and it leads me to 2 out of the 3 strands in the web of dualities. The third strand, the Bose-Bose duality, is a little bit more intricate, but I don't think that there's much to be learned from repeating the same exercise of coupling the theory to an external gauge field, then promoting that external gauge field, which is non-dynamical, to a dynamical gauge field, then coupling that through a BF coupling to another external gauge field, and then bosonizing that theory. Okay, so that's basically the same game that we're playing. There's a couple of subtleties involved in the Bose-Bose construction, but it's not going to be particularly important. And by the same token, I don't want to spend too much time in this lecture talking about all the different strands of the Fermi-Fermi duality. Sorry, of the 4-dimensional duality web. The main player here, again, is going to be bosonization. And as I said the last time, it's not so much that bosonization is like key, sorry, is the only starting point. Any one of these dualities works perfectly fine as a seed. Bosonization happens to be the one that's most clean to understand, and so that's the one that we focused on in our work as well. So I'm going to talk about 4-dimensional bosonization, which is a little more tricky to work with than 3-dimensional bosonization, largely because it results in a non-local theory. And then I'm going to talk if I get time, I'm going to talk about one of the other two strands, and I think it will be the Fermi-Fermi strand as well in the four-dimensional case. And this will again lead to a subsequent web of four-dimensional dualities. It's not nearly as well understood as the three-dimensional web, which had 4 years worth of development following its discovery in 2016. But I'm hoping that it's sufficiently interesting that more people will pay attention to the four-dimensional version. And there's some good physical reasons for thinking about this as well. And on that note, I'd like to start off today's discussion by introducing some of the physics underlying what we're doing here. Okay. So, okay, technically I should really say theta terms in electrodynamics. All right. So what do I mean here? So this is a interesting and rather beautiful story, actually, that we take for granted in much the same way that in my introductory lecture, I said that we take the idea of electric-magnetic duality in 4 dimensions for granted because it's so prosaic, because it's so kind of, so what? So let me start by saying the following. And now I'm working in 4 dimensions, and this lecture is going to be pretty much entirely taking place in 4 dimensions. So 3 space, 1 time. So if I impose the following 3 conditions, I want a theory to be linear. I want my theory to be gauge invariant. And I want the theory to be relativistic, in other words, Lorentz invariant. Sorry. Linearity plus gauge invariance plus Lorentz invariance for a theory of bosons, or vector bosons, so spin 1 particles, necessarily leads to an action that most of us are familiar with, and this is the Maxwell action. The Maxwell action is a functional of the electromagnetic 4-vector potential, which contains the scalar potential and the vector potential. And it's a 4-vector in space-time. And in some system of units, the action looks like minus a quarter F mu nu F mu nu. So this may be familiar to pretty much everybody in this room, at least. And it's just the Maxwell action. The 1 over mu naught is the permittivity of free space. It's a particular unit convention. This F mu nu is the Faraday tensor, or the field strength tensor, and it contains as its components the electric and magnetic fields. And if I write it out explicitly in electric and magnetic fields, then this action takes the form that you're probably familiar from first year already, epsilon naught over 2 e squared minus 1 over 2 mu naught p squared. Okay. Again, the epsilon and the mu are not really the important things here. The e squared minus b squared, this particular form of the action is important. And the key thing here is that if you look at the variation of this action with respect to a mu, then the equations of motion, the Euler-Lagrange equations of motion, are nothing but the Maxwell equations. So in other words, if I go delta S Maxwell by delta A mu, and I set that equal to 0. So this is the variation of the action with respect to the 4-vector potential. I get Maxwell's equations. So this is a very clean, compact way of writing down Maxwell's equation. And in fact, my statement was the conditions of linearity on my theory, gauge invariance of my theory, and Lorentz invariance imposed the Maxwell equations. It's the simplest action that I can write down that respects these three conditions in 4 dimensions, provided I'm thinking about a spin-1 theory, right? A theory of spin-1 fields. Okay. The question is this the only action I can write down in 4 dimensions that satisfies these conditions and that's built out of the electric and magnetic fields that occur quadratically in the action? And by quadratically, I'm talking about these factors of 2 here. Okay, so E occurs in E dot E, B occurs in B dot B. They occur quadratically in the field, right? And the answer is no, actually, it's not. And the reason it's not is because in 4 dimensions, and 4 dimensions is special in this regard, in 4 dimensions, we make the observation that, so in D equals 4, the Hodge dual of a 2 form, namely F mu nu, is another 2 form. And this follows from the fact that 4 minus 2 is 2. Okay. And in fact, we can define the dual form, which I'll call the dual field strength, F star F mu nu. I'm going to define this guy as a half epsilon mu nu lambda sigma F lambda sigma, where this epsilon tensor is the completely antisymmetric tensor in 4 dimensions. Okay. Sorry, let me just mute new entrance. Okay, so right, that's the dual field strength tensor. Okay. Let me just check something. All right. So if I look at this, so F mu nu contains the electric and magnetic fields. So if I look at the structure of F mu nu, it's a 4x4 matrix. And the elements of that matrix are the electric fields on the top row and the leftmost column, and magnetic fields sitting in the remaining 3x3 rows and columns. And because of the anti-symmetry of F mu nu, everything on the diagonal, of course, has to be 0. So that's the structure of F mu nu. What about star F mu nu? So in fact, it turns out that if you go ahead and calculate component by component, component by component, what the elements of star F mu nu are, you'll find that it can be derived from the components of F mu nu by simply making the exchange electric field with magnetic field and magnetic field with minus the electric field. So we can find let's rewrite this. Derived the components by mapping the electric field and the magnetic field to the magnetic field and minus the electric field respectively. Okay, so if you start off with F mu nu, you exchange electric field with magnetic field, and magnetic field minus the electric field in units of C equals 1, you'll get star F mu nu. You get the components of star F mu nu. Well, this results in a whole other term that you can add to the Maxwell action called the theta term. And the theta term action is theta, again, is also a function of A mu. And this guy is theta E squared over 4 pi squared H bar integral d4x a quarter star F mu nu star F mu nu. And I'm using Einstein summation here, so every time you see a repeated Greek letter, you sum over it. So star F mu nu, star F mu nu means star F mu nu 0, 0, F0, 0, plus star F mu nu F0, F0, 1, F0, 1, etc. Okay, so that's what the summation means. Well, my claim is that this action is also Lorentz invariant. It's also gauge invariant, and it's also quadratic in the fields. And finally, it's also linear. So why don't we normally, in fact, you can do the calculation quickly, and you can show that this guy takes the form theta E squared over 4 pi squared H bar integral d4x E dot B. So it's quadratic in the fields, and it in fact contains a term that goes like the electric field dotted into the magnetic field. All of the slew of this, again, I'm working in units of C equals 1, so there's definitely C sitting in here as well, but all of the slew of constants like the electric charge, H bar, etc., that follow the theta around are there to ensure that the theta is a dimensionless parameter. So this guy is a dimensionless parameter that I get to choose the value of. Okay, I should say that my treatment of this, my discussion of the theta terms follow from a couple of different sources, including David Tong's notes on gauge theory, where there's a very nice discussion about the physical consequences of said theta term. But you can find it in any textbook on quantum field theory and quantum electrodynamics. Okay, so why don't we pay more attention to said terms? I mean, if you've done a course in electrodynamics before, you probably haven't seen this theta term, nor discussed its consequences. Why, when we solve the Maxwell equations or the wave equation that follows from the Maxwell's equations, don't we pay much attention to this term? Well, the reason we don't pay attention to this term is because the reason we don't pay attention to this term is because with a little bit of manipulation, you can show that the term is actually what's called the theta term is a topological term. I'll tell you what this means in this context now. But what it means is that I can take this theta term and with a little bit of manipulation and integrating by parts, I can put it into the form theta e squared over 4 pi squared h bar integral d for x d mu of epsilon mu nu lambda sigma a nu d lambda a sigma. The fact that I can write this thing as the derivative of something means that this guy here is what you would call in first year calculus a total derivative term. And the integral over something, in this case, a space-time manifold M, of a total derivative can, by the fundamental theorem of calculus, be turned into something, into an integral over the boundary of M of the something itself. So this epsilon mu nu lambda sigma a nu d lambda a sigma. What does that mean? Well, what it means is that this term only depends on the data specified on the boundary of space-time. And typically, if you've hung around this area long enough, you know that we tend to discard, we tend to ignore such boundary terms by engineering effectively. And the way we do this is to either engineer the boundary conditions. So if we demand that all the fields vanish sufficiently fast, far away from the origin, then we can engineer that this boundary term doesn't give me any contribution. Or by working on a manifold without a boundary, we can effectively just set this term equal to 0. Either way, we tend to ignore boundary terms in physics. Okay, so we tend to ignore boundary terms, and because they require data specified on the boundary, these are what's called topological terms. So they contain global information about the space-time and nothing local, no local dynamics. In other words, the theta term does not contribute to the dynamical system. And that's why we tend to ignore it. That's why you probably haven't seen it up until now. Okay. However, that said, it's important to note that there are various situations in which there's actual physics contained in S theta. One such system is what's called a topological insulator. So one system in which S theta is crucial, not even important, is in the physics of what are known as topological insulators. These are actual materials. They're not theoretical. They're very much studied actual materials, and some of them that come to mind are, for example, bismuth telluride, Bi2Te3, or bismuth selenide, which have the properties of these topological insulators. And among the properties of topological insulators is the fact that the bulk of the material, so imagine a block of this kind of material, the bulk of the material is insulating, but the surface of the material is a conductor. Okay, these are a remarkable class of materials that we're only now starting to discover, and largely we're starting to discover them because of the understanding of the role that gauge theories play in such materials. Overall, the umbrella of the class of materials that we're considering is what's called ultra-quantum matter. And in these materials, not only does the theta term play a role, but a very specific value of theta plays a role. And in these materials, theta equals pi. Okay. So this is just a short introduction to the idea of topological insulators, and specifically the theta term that's going to be important for what we're going to discuss now. I'm not going to say any more about theta terms and topological insulators. This is a beautiful physics that I would love to say more about, but I don't have the time to do so. Any questions at this point? No? Okay. If you do have questions, please unmute yourself and ask at any point. Okay. So then let's talk about extending the duality web to 4 dimensions. So our goal will be to try and extend what we said in the last lecture 1 dimension higher and arrive at a 4-dimensional duality web. Now, to do this, I'm going to need a 4-dimensional analog of 3D bosonization. That was the seed for the 3D duality web. And I'm going to progress by taking it as a seed, or its 4-dimensional analog as a seed for the 4-dimensional duality web. Fortunately for us, a 4-dimensional bosonization duality was derived by Burgess and Quevedo some time ago already. So 4D bosonization as a duality was derived already by Burgess and Quevedo. And we're going to be following what they did in some detail. So bosonization can be extended from 3 dimensions to 4 dimensions. And if you remember, the other 2 legs in this 3-dimensional duality was particle-vortex duality, which is a boson-boson duality, and fermionic particle-vortex duality, which is a Fermi-Fermi duality. Extending particle-vortex duality to 4 dimensions is a little bit more tricky than extending bosonization to 4 dimensions. And the reason for this is because the underlying particle-vortex duality is the fact that in 3 dimensions, a scalar, which in the language of differential geometry we would call a 0 form, is Hodge dual to a 1-form gauge field, right? While in let me expand on that. So what about particle vortex duality? And for this, I make the statement that in 3 dimensions, a scalar, which is a 0 form, is Hodge dual to a 0, 1, 3 minus 1 is 2, so it's 1 form. It's dual to a 1 form gauge field. Okay, while in 4 dimensions, a scalar is dual to a 0, 1, 4 minus 1 is 3, a 2 form. So, but in 4 dimensions, a scalar is dual to a 2 form. Something that looks like b mu nu, where b mu nu is minus b nu mu. So it's antisymmetric in its indices. Okay. The thing that something couples to is the object of interest. So if I have a 1 form gauge field, that 1 form gauge field, a mu, its role in my theory is to be integrated over. And I integrate a 1 form gauge field over a line. And that line is the world line traced out by a particle. So if I have a particle like this, then as it moves in space-time, it traces out a world line. And that world line is sigma, and that is the same sigma that I integrate out over here. And I integrate a 1 form over a 1-dimensional object. And that 1-dimensional object is the world line of a particle. So that's where the particle comes from. So this particle is what's dual to the vortex. In 4 dimensions, a scalar is dual to a 2 form. And a 2 form couples to a string-like object. So this seems to suggest that in 4 dimensions, we don't have a particle-vortex duality, but we have something like a particle-vortex string duality. That kind of makes sense because a vortex in the plane is a string in space-time. This is a vortex string. It's a soliton. It's not a string as in string theory, which is a fundamental string. This is what we call a solitonic string. Okay, and this line of reasoning was precisely what was conjectured by Beekman et al. In a wonderful paper extending particle vortex duality to 4 dimensions. However, it's not the approach that we're going to take. So our approach was inspired rather by a recent paper of Palumbo, which conjectured a Fermi-Fermi duality in 3+1 dimensions. And that's going to be the starting point for what I want to discuss. So Palumbo's duality works like this. So it says the following. Again, the language is going to be very similar to what we've been working with in 3 dimensions. Okay, but it says the following. If you start from a massive Dirac fermion coupled to a U1 gauge field. So we start from S1, which is a functional of a massive Dirac field psi coupled to a U1 gauge field a mu. And the action looks like integral d4x psi bar d slash psi, and this is the gauge covariant derivative with respect to a, plus m psi bar psi. And because this fermion is massive, I can integrate it out in the functional integral by using its equations of motion. And if I integrate out the fermion, then I get an effective action, which I'll call S1 effective. And S1 effective doesn't have any dependence on psi because I've integrated it out. So it's only got dependence on a mu. And when I do this integral, I get another effective action 1 over 32 pi integral d4x epsilon mu nu lambda sigma f mu nu f lambda sigma. So now it becomes clear why I spent time talking about theta terms, because this is precisely a theta term contribution. Here's the f mu nu star f mu nu, or star f mu nu contribution sitting right here. Okay, epsilon mu nu lambda sigma f mu nu is nothing but star f lambda sigma. So star f lambda sigma multiplied by lambda sigma integrated over gives me precisely this theta term contribution. And in fact, you'll see that there's a factor of 1 over pi here as opposed to 1 over pi squared, which tells me that this is a theta term for which theta equals pi, which makes perfect sense because, in fact, what Palumbo was trying to do was give an understanding of 3+1 dimensional topological insulators. But where's the duality in here? So again, Palumbo started off with an action for a massive Dirac fermion coupled to a U1 gauge field. So let's put that in. So this is a massive Dirac fermion plus a U1 gauge field. Okay. The U1 gauge field is not dynamical, therefore you don't see any f mu nu terms here. When I integrate out the massive fermion, I get an effective field theory for the A mu's, and that's a topological theory, as we just discussed. Similarly, if I start off from a neutral composite Dirac fermion, so if I start from a composite Dirac fermion coupled to a dynamical gauge field, give me a second, coupled to a dynamical gauge field, let's say little a mu, and a two-form f mu nu, then I have the following story. Here, I'll start off with some action S2, which is a function of capital psi, little a mu, capital A mu, and a two-form b mu nu, which looks like an integral d4x psi bar d little a slash psi plus m psi bar psi. That's the mass term for the Dirac fermion, minus 1 over 8 pi epsilon mu nu lambda sigma b mu nu f rho sigma, lambda sigma plus little f lambda sigma. I'm just going to write out all these terms and then I'll tell you what these are. And this is the last time I'm going to write down all the indices because, as you can see, they're a pain in the butt to write down. And the context will tell me what the indices are in future. Okay, so here's my big, complicated looking action. Okay, let's unpack this a little bit. This guy here, F, is the field strength of the non-dynamical gauge field, capital A. Similarly, little f is the field strength for the dynamical gauge field, little a. B mu nu is a two form. Epsilon is the antisymmetric tensor. This guy, chi, is a dimension 2 parameter in the theory that controls the coupling of B. And H is the field strength of the two form. So H is dB. And for those of you who are familiar with the language of, so this is fermion mass. Those of you who are familiar with the language of differential geometry, you know that the exterior derivative operator takes a p form to a p+1 form. And so D takes a 2 form to a 3 form, which carries 3 indices, mu, nu, lambda, sigma. That's what the H is. So then, said Palumbo, what you do is you integrate out the massive gauge field. And if you integrate out psi, if you integrate out psi, then you get another effective action, which we'll call S2 effective. And S2 effective, as you may imagine, is an action for A, little a, and B mu nu. And technically, I should put some indices here. Okay, and this is the integral d4x epsilon. Again, I'm not going to put indices. Epsilon carries 4 indices. 1/32 pi, capital F, little f, each of which carries 2 indices. They're contracted in the obvious way with epsilon, minus 1/8 pi, b, contracted with the first 2 indices of epsilon, capital F plus little f, contracted with the second 2 indices of epsilon, plus the same 1/32 pi squared chi h squared. Now you make an approximation, said Palumbo. You can, in the low energy limit where chi goes to infinity, you can ignore this term, drop the kinetic term because you send chi to infinity, and that term doesn't contribute relative to the other terms. In which case, b mu nu effectively just acts as a Lagrange multiplier in this term. So this guy acts as a Lagrange multiplier because it's no dynamics anymore. And the Lagrange multiplier enforces the fact that capital F plus little f equals 0. In other words, capital F is minus little f. So I can just substitute into the equations of motion. And the upshot is that once all the dust is settled, S2 effective, remember, was the effective action for a Dirac fermion coupled to a dynamical gauge field coupled to a two-form field, is equal to the effective action for a massive Dirac field coupled to a non-dynamical U1 gauge field. That's the version of duality that Palumbo was advocating for. And in fact, this provides, via this integrating out the gauge field, a duality between a fermionic theory in 4 dimensions and another fermionic theory in 4 dimensions. And in fact, you can go a little bit further, because you can show that at the boundary of this 4-dimensional spacetime, the effective action, so at the boundary of 4-dimensional spacetime, so at the spacetime boundary, S1 effective of A mu takes the form S Chern-Simons of A on the boundary. Okay, and this is the effective action for a Dirac fermion coupled to A. While S effective 2, or S2 effective of A, and B, which is a two-form, is nothing but S Chern-Simons BF of A, and little b, where little b is related to capital B in some way that's not particularly important. In other words, this Fermi-Fermi duality descends on the boundary of the 3+1 dimensional space, descends to a Fermi-Fermi duality in 3 dimensions. And Palumbo wanted to conjecture that actually this descent relation is precisely the Son's conjecture that we spoke about in the last lecture. However, and this was our starting point, it is not. So everything that was just said is true, but this is not the same as Son's conjecture. And the reason why it's not Son's conjecture is because in Son's conjecture, which remember was trying to explain particle-hole symmetry in the lowest Landau level, there, the BF coupling between the emergent gauge field and the external field, little a and capital A, is not the same as what exists here. In other words, it's not the same as this Chern-Simons BF coupling. So our approach was to start a little bit differently. So we started with the with 4-dimensional bosonization. Let me see how much I should actually mention in this story. Okay, I'm not going to, so the rest is fairly technical. I have 6 minutes remaining. Okay. So let me make a sketch of what we did then. And I'm happy to answer anybody's explicit questions about this, should they have any. In 4 dimensions, what we did was to follow our strategy from 3 dimensions. And in particular, we add terms that are the analog of the Chern-Simons terms and the BF terms. And in our case, we add terms that are theta terms, and then promote external gauge fields to dynamical gauge fields, then integrate out those dynamical gauge fields to arrive at a 3-dimensional version of duality, bosonization. So, sorry, 3 plus 1-dimensional, 4-dimensional. Bosonization duality. From the 4-dimensional bosonization duality, we apply the 4D bosonization multiple times to derive a 4-dimensional boson duality, which is the analog of a particle vortex duality. And then apply bosonization with its time-reversed counterpart, or a variant of its time-reversed counterpart, to reproduce an analog of Palumbo's duality that I just covered for you just now, which is a 4D Fermi duality. And these three together constitute what we think is a 4-dimensional web of dualities mimicking what happens in 3 dimensions. And in fact, we could do a little bit better and take the 4-dimensional spacetime, which is 3 space, 1 time, take one of those dimensions and curl it up to get a 3 plus 1 dimensional spacetime. And by dimensional reduction, we showed also that the 4-dimensional spacetime duality web descends to precisely the 3-dimensional duality web that we spoke about in the last lecture. However, there are some caveats that are important in here, which is that in the 4-dimensional case, not only did we have to take the low energy limit, in other words, where E squared goes to infinity, but there's another more singular limit that comes in specifically the boson-boson duality. So this duality is singular in a way that we don't quite understand yet, but that might have to do with the anomaly structure of the quantum field theory. Let me finish off then with a discussion of let me finish off with a discussion of some outstanding issues that I'm still thinking about as current projects, which, if anybody's interested, I'm happy to talk about in person, one-on-one. So some outstanding issues then. Are the following. The first is that three-dimensional bosonization was quite recently, well, so after the duality web was realized in 2016, it was quite soon after that that it was realized that this whole three-dimensional web structure descended from what's called three-dimensional mirror symmetry. Three-dimensional mirror symmetry is a very powerful type of supersymmetric duality. So everything that I've been talking about so far, everything, all the dualities that we've been talking about are non-supersymmetric dualities. And they take place at low energies in quantum field theories in low dimensions. So the statement here is that the 3D duality web is related to so-called three-dimensional mirror symmetry. Three-dimensional mirror symmetry relates a free chiral superfield to essentially n equals 2 supersymmetric QED in 3 dimensions. Okay, so this is a well-known, well-studied duality in supersymmetric quantum field theory. You map a free chiral superfield to this n equals 2 supersymmetric QED with a single charge superfield. Then what you do is you take the supersymmetric theory and you break the supersymmetry by adding what's called a D term. So you deform the supersymmetric theory a little bit, and you let the theory flow to low energy, to what's called the infrared. And when you do that, you find precisely three-dimensional bosonization. In other words, you start off with a supersymmetric theory in which basically there's one duality. You deform this theory and you let it melt and flow to low energies, where it becomes three-dimensional bosonization, and where three-dimensional bosonization is the seed for this three-dimensional duality web. So essentially, the statement is you can derive all of the dualities from the three-dimensional duality web from three-dimensional mirror symmetry, this supersymmetric duality. So what does this got to do with our story? Well, in our story, the following observation can be made. Three-dimensional superspace that you utilize in this 3D mirror symmetry can actually be derived from an n equals 1 superspace in 4 dimensions. In other words, less supersymmetry in more dimensions. So you start off with this n equals 1 4-dimensional supersymmetric theory. You can dimensionally reduce it to the n equals 2 supersymmetric theory in 3 dimensions. And everything else follows as I said. So if 3D mirror symmetry can be derived from a 4-dimensional supersymmetric theory, and the 3D duality web in some sense derives from the 4-dimensional duality web by dimensional reduction, could it be that the 4-dimensional duality web could be realized in a similar way from a 4-dimensional supersymmetric theory? So this would be remarkable because 4-dimensional supersymmetric theories we know, we understand, we love. The dualities there are called Seiberg dualities. There's huge literature on Seiberg dualities in 4 dimensions. And it would be a beautiful relation to try and understand whether 4-dimensional non-supersymmetric duality web is derivable in the same way. The second thing is that this wealth of information that was provided by 3-dimensional duality webs resulted in the prediction of novel, new, gapped phases of matter in 2+1 dimensions. So the question then arises is, can we use this 4-dimensional duality web to predict novel, exotic, gapped phases of matter in 3+1 dimensions related to 3+1 dimensional topological insulators, for example. And then finally, it's worth noting, and I think I did note it in my last lecture, that you can start off with a 3-dimensional duality web and dimensionally reduce that to realize a lot of the well-known, well-studied, well-understood 2-dimensional dualities that already exist in either the condensed matter or the high energy physics literature, going back to the 1970s already. So starting off from 3 dimensions, you can go to 2 dimensions. Starting off from 4 dimensions, you can go to 3 dimensions by dimensional reduction. So then the question is, can you join all the dots and put together a full interdimensional, at least in the dimensions 4, 3, and 2, duality web? This, I think, would be a beautiful way to encapsulate these really rich relations between low-dimensional, non-supersymmetric theories in 4 dimensions, in 3 dimensions, and in 2 dimensions, with real-world applications that extend beyond, high-energy physics to condensed matter physics, for example. And with that, I would like to end and thank you for your attention. Any questions?